All right, folks, welcome back. Today, we are going to start with this topic, which is deconvolution. Convolution. And we'll see why in a little bit. So you remember we said that if you take a giant image of a cat, and here's your cute cat, and this cat, you pass it through a convolutional neural net. What is each layer of the convolution made up of? It is made up of, the first is a stack of convolutional filters. A stack of convolutional filters, isn't it? You can take, for example, so this image comes in 3 channels. What are the 3 channels? Red, blue, green. Right? It will have, so the structure of this data would be, it will have a certain height, h, it will have a certain width, and it will have 3 channels, height, width, channel, right? This is 3. This could be, pick your number. Let's say that it is 128 pixels, and this is 128 pixels. Something like this, right? You take an image, you pass it through filters. Let's say that you pass it through 6 filters, right? What will you end up with? You will end up with an image, and let's say that you take a filter size of 3 by 3, and you put in padding. Do we remember why we put padding later on? We don't put padding at this layer. What comes right after the convolutional filter? Padding. Activation, and then pooling. Pooling. You do the pooling, right? Are we together, guys? Right. So if I represent the filter with k, you would say that you do k.x, you activate it, right, and then you apply the pooling operation on it. What are some of the forms of pooling we learned about? Max pooling, min pooling, average pooling, and so forth. And we talk about the use cases when each of these is a good idea, right? Now, one of the effects of this process is that you can, if you attach some padding to it, you can preserve the size of the output, isn't it? The feature map that comes out of it, through all of this, you get a feature map of, again, size, h prime, width prime, and k channels. Let's say that the number of channels is c prime. C prime channels. If you use C prime filters, C prime could be 6, for example, then you would end up with 6 feature maps. So far, so good, guys?
I don't remember you going to buy. Yeah, only we talk about polygons, right?
No, yeah, padding I didn't talk about. Okay. I did. See what happens. So let me go through that padding now. Suppose I have an image. Okay. Let's talk a little bit about padding. Suppose you have an image that is, let's just for the sake of argument, take 5 by 5. 3, 4, 5. Is this 5 by 5? It looks 5 by 5. And you apply a filter that is 3 by 3. You apply a 3 by 3 filter, right? Do you realize that you'll end up with a feature map that is smaller? Right? Why? Because this is one part, this is another part, this is the third part, and then you have nowhere to go. Right? So you would end up with a feature map that is just 3 by 3. But you see, it becomes smaller. But what happens if I just go and pretend that this image was actually larger? And I can just fill it up with zeros. There are many ways to do it. Pick whatever arbitrary rule you want. You can fill it with ones. Like if you notice that most of the picture is white, fill it with 1. If you feel most of the picture is 0, fill it with 0. Dark, fill it with 0, or fill it with average, or whatever you do. Just fill it with some constant value, right? Though it's customary to just pad it with 0. Then what happens? Now let's see how many boxes we can create. 1, 1 here, a 2 here, right? A 3 here, 4 here, and 5 here. So your feature map therefore will be 5 by 5. The feature map that comes out will be 5 by 5, guys. Does it make sense? Do you see that? You just took the image and you put a border, a frame around it, frame of zeros or ones before you applied the filter. Am I making sense? And then what happens is you have preserved the size of the filter. Preserved the same size as the input to the conv layer. Right? The convolutional filters, or let me just say con filters. Does that make sense, guys?
So this has to come on the way from the
Before, yeah. So what you do is you take the image, you pad it, and then you go about with the filters. And when you apply the filters, you end up with this. Why would you want to do that? Because you choose to. There are situations where you say, hey, I want the output to be the same size as the input. Right? It is just one of the tricks in your bag. There's nothing magical about it. Right? You can just apply padding. So, sorry, I didn't talk about padding. And how much padding you apply is totally up to you. You can apply 1 layer of padding. You can decorate it further with 2 layers of padding.
So if you don't apply the padding, do we lose anything?
Your image just gets shorter.
Image is very short.
Yeah, which doesn't mean necessarily that you lose anything.
Yeah.
Right. So it's just that. So this is padding. Right.
So a quick thing, Asif. So you say like you have only a 3 by 3 padding on a 5 by 5 or probably a 6 by 6 image, basically at this point with padding. Right.
Yeah.
So how do you get a 5 by 5 out? I saw the 5 things you moved out, but there's only a 3, right? 5 by
think
6.
about it this way. Let's go through this. This is 5 cross 5.
Yeah.
Let's take it. If I add 1 layer here, 1 layer here, now this outer box, what is it?
7 by 7.
It's become 7 cross 7.
7 cross 7. Yes.
Right? And then when you apply this 3 by, you can convince yourself that now the output of that will be again 5 by 5.
Okay.
Right? You want me to do it step by step? I think I'll let you do it on your own, because let's move forward a little faster. Okay. But you can see that it will become 5 by 5 again. Right?
Okay.
Then out of this 5 by 5, of course, the moment you apply max pooling, let's say, what it will do, it will reduce the size of the image. It might become, I don't know, pick your number, what it will become. Let's say it will become smaller. I'll just use the word smaller. Depending upon what's your stride, what's your pooling, and whatever it is, it will just become smaller. So what happens with typical conv layer is, you notice that in the beginning, you have big feature maps in the early layers, feature maps, right? And fewer channels, like you will start with 6 or, 4, 8, 6, whatever number of channels, a few channels. And of course, in the beginning, you start with just 3 channels, RGB. And progressively, as you go down, what happens is that your feature maps become tinier, smaller. Feature maps, but you use a lot more filters, lot more channels. Are we together? So a large number of channels. This is a general tendency. Look into all the architectures that I asked you to review, LeanNet, AlexNet. You will see that everywhere this behavior is there. Right. And why is this behavior there? Just to recap, see what you're doing is at the end of it, The goal is very intuitively for each of these things to say something very abstract about the picture, right? Give some abstract description about the picture, and you end up with lot of abstract, a feature, lots of abstract feature representations. Right? Are we together? What those abstract features are doesn't matter, but those abstract features, in effect, describe this image. Right? So that's what it is. And then, of course, you flatten it, you pass it to flatten, and from flatten, you feed it to feed forward layers, a few feed forward layers, and then you do whatever you want to do for classification. You can pass it to a softmax. So this architecture, I hope, guys, tell me that this is now clear to all of you. Are we clear about this, guys? Have you reviewed? If you have been reviewing ConNet in the last couple of weeks, this should be very straightforward. We are going to now talk about the topic of, and for reasons, just because it's fun to do so, can we go from these abstract features back to, like, can we take the reverse journey? Suppose I were to give you lots of these abstract features, lots of it, right? Let's say 128 of these abstract features. Can you, just as an intellectual game thing, can you just take one feature map, small tiny feature map? Can you go from this to a bigger feature map? Is it at all possible? How would you do that? Like, suppose I gave you something like just a 2 by 2. Sorry, let me take a 2 by 2, a tiny feature, because at the end, that's about what it comes down to. Something small, right? Pick your numbers. Let's say these numbers are usually fractional numbers, like 0.2, minus 0.3, something like that. But let us talk in terms of integers, because it will be easy for us to play with. Yeah? So remember that they are fractionals typically. Let us pretend they are integers. Why? Because we can do arithmetic more easily with integers. So should I just take 1, 2, 3, 4 just for fun? Right. So now you realize that every time we apply a filter and we do pooling and all of that and activation, you end up with this. But how can we end up with a bigger, let's say from this, how can I go to a bigger feature map? Somehow, how can I reverse the process? So the terminology that people say is you have a big image, right? Each feature map it is extracting one sort of specific thing. Each filter is looking for something specific, right? Remember, what was the filter looking for? Edge, this, that. I come here, I have this feature map. Now, just take one. Is there a way for me to undo it? And roughly speaking, say, I was just an edge detector, right? But I can tell you in the bigger picture, this is where the edges were. Are you getting the understanding? So I have this little representation, and I'm saying that from this, I know that in that big picture out there, because I convoluted from that, this is the shape of the edge there. If only I could, because I'm the edge filter. Does that make intuitive sense? Is it making intuitive sense? No, forget about how we do it. I'm asking a logical question. Yeah. If I am the edge detector and I have a high resolution picture here, I am the edge filter. I just went scanning over the image and I came back with this tiny feature map. If I were the edge detector, my feature map therefore contains the edges. The information of the edges is here, right? Somehow in an abstract form, it is here. Do you agree or not? Right?
It will
So
survive the convolutional layer, but how will it survive the pooling layer?
no, forget about that. I'm saying forget about the implementation details. Look at it mathematically. I have done a bunch of mathematical operations. I have gone from a picture, my cat, right? A very colorful cat. And from this, I have come up with this little thing. If my job was just edge detection, right? Remember, I used that edge detector filter. I think, what did I take the value as? I think 8 minus 1 minus 1 minus 1 minus 1. And then I did my scanning and activation and blah and blah and blah. One of the questions that I can ask is, to what extent it is invertible, right? Can I, in some sense, go back, right? It should be invertible, isn't it, in some sense? So how would you, what are some of the tricks you can use to basically go back? Right? So in principle, at least one can ask this question that if this is f of x, then there should be a way to do f inverse of x. Roughly speaking, some operation that is not exactly inverse, but that is approximately inverse of it. That much we can ask, right? There should be some machinery to invert it.
It would need more information than what it currently has.
That is all right. So you sort of Vasanti says that we have lost some information along the way. This filter doesn't know, but remember there are other filters, right? They can all collaborate in restoring it. But this filter can just tell see, it may not restore the whole image. It will just say, I will give you the big image, but only the edges in the big image, because I only know the edges. Right? Other filters were looking for something else. They can fill in the big image with other information, but I was just the edge detector. I will tell you how to get back to the edges in the image, not the whole image.
So then it has spatial information?
Of course it has spatial info.
Asif, is it called transpose?
So let's not go there, right? If you, yeah. Yeah, you're trying to say that, see, I was only one filter. I'm not saying I'm going to answer just magically because I was just the edge detector, but I can guess the entire image. But I can guess the edges in the entire image because that's what I was hunting for. Right? That has to be there. And so the process of doing that, there are many ways of doing that. So now the way you look at it is, see, this process produced a smaller feature map. Right? If you look at only one feature map of the many feature maps that you produced, it is a small feature map. So you say that this feature map, in some sense, has subsample. It has taken only one thing out of it, some things out of that. Right? So there has to be a way back to somehow oversample and go back to the original image, but not get a full cat, but maybe just get, this one will get only this part out. Right? And the other filter will fill in something else. Another filter will, another feature map will go back and invert itself to something else. And this picture can be to some extent restored.
So Asif, basically it is acting as an encoder decoder kind of.
Yes. So guys, those of you who have taken my deep learning courses and know all about the encoder decoder, hold your thoughts. I'm trying to motivate people who are learning it for the first time. Right? So does this make sense, guys?
Asif, so I can see that the edge detectors and different filters would probably give, yes, I am a edge, or I'm a circle, I'm a straight line, but would it, I'm wondering if it would maintain the relationship between those, saying that, you know, this particular circle was at this, at the top of the image,
Yes.
or the bottom of the image. Yeah.
Yeah, it does. Because this feature map, see, guys, tell me, if this was an edge detector, look where I'm coloring it. If this place is completely lit up, what does it mean? Somewhere near the top of the image was an edge. Does this make sense or not? Yeah. So your feature map preserves the spatial relationship. That is the whole That is the whole beauty of the feature maps. They are very spatial information preserving machines, right?
So in that case, then it would be able to then kind of
It would be able to invert it. So now what I'm going to do is tell you how it is. So there are many ways to sort of invert the convolution. So I will use the word invert or undo, opposite. And I'm deliberately using very colloquial terms, opposite of conv, filter, convolutions, right? Here is a trick. There are many, many tricks that people came out with, because the moment you realize that mathematically there is no reason why we cannot do that. If you look at feature map, it is spatial information preserving. Therefore, there has to be a way to invert it.
So just a quick question. It's not just the feature map, right? On this, you have applied the activation function. So does it mean all of these activation functions are also inversible functions?
Yeah, what you are saying, see, remember what I'm saying is I need a G that is an approximation of F inverse. I'm not saying that I necessarily need completely invertible functions, right? It doesn't have to be an exact inversion. I just need to produce by a process something else. So for example, how should I say it? If it was a golden retriever, it's something like a Labrador. Right? I'm joking, but a close. See, remember, guys, in neural networks, you always try to approximate some other function which will do the job. You don't have to need mathematically a exact inverse function.
So,
Does that answer your question? Yeah?
so I know that there are like n number of feature maps, right? And in each feature map will have some some form of the source of truth of that particular image. So when you inverse them, the inverse convolution, so how it will maintain the order of the image? So
You
that
don't know. There is no order. Remember, the filters don't have each feature map produces something. You need some way to compose from all the feature maps and their inversions the original image.
Yeah, so how it will get the original image when you
So that you will see how.
Yeah.
Come again?
Why do we have to do the?
Oh, because it's a nice, fun, intellectual game. Why not? In math, you always ask the question, why should we do something? Hey, why not? Tax dollars at play. Research. I'm sorry, I'm kidding. In my graduate school, there was we used to work on very abstract things. We used to puzzle over what is happening on the edge states of a black hole, like on the on the horizon of a black hole, right? So the black hole has apparently this edge, and if you go over the edge, there's no coming back. It's called the event horizon. So you used to think what's happening there, and most people would say, "Why don't you worry about what's happening in your city and your Earth?" Right? So the joke was that because all of this research was funded with tax dollars, somebody put a poster, a grad student put a poster on his door. He said, tax dollars at play. Right? So guys, to answer your question with me, see, the way the field always works is when you are an engineer, you always say, what in the world is the purpose of this? Generally, those are bad ways to come up with creative ideas. The most creative ideas come in research when you ask, can I do this? And you never ask, why in the world would I do this? What benefit is it? You first ask, can I do this? Oh, I did this. And then you ask, okay, now that I did this, what can I do with it? Right? It's a different way of looking at it. But anyway, what we can do with it is something very, very practical. In fact, we're getting there.
Asif, does this kind of set the framework for like generative stuff then?
Yeah, guys, you're getting carried away. The answer to that is yes, but let's not get there. I want you to be laser focused on understanding that I can, from the filters, I can sort of go through the opposite process and get some semblance of the original image. Why I want to do that? What will it produce? All this encoder decoder, because you guys have heard about all this. Suspend your judgment. Understand this. Be sure you get this. Are we getting this? That theoretically, there's no reason we can't do this. I'm going to show you one way to do this. But the simple answer to your question, Bhavin, is yes, and we are going to go there. That is the topic of the next week. From next week, it's all generative AI. So now, any questions, guys? I hope you understand that nothing prevents me from writing nothing. Now, the whole question is, how would I do that, though? It's very easy to say, oh, from a feature map, I can make a bigger feature map, right? But how? So there are many ways that researchers came out with it. Some of the ways that people came out with it were oversampling. I won't go into it. That often meant sticking in lots of zeros in here and there. And I mean, there were things that people did, right? And after a lot of experimentation, let me just say, this is one way. And there were many other ways tried. But the way that sort of became efficient and more or less the de facto standard, right, is called transpose convolution. Transpose convolution. Now, there is a bit of abuse of vocabulary. Many people call this deconvolution. But actually, even though colloquially you can call all of these methods that do the opposite of convolution as deconvolution, because that seems so logical to call it deconvolution, isn't it? Actually, you shouldn't use the word deconvolution, because it turns out that there was actually a very specific method that was named deconvolution. And we don't use that. We instead use transpose convolution. Are we together? So when you're thinking deconvolution or the opposite of convolution, in code, what you should actually use, and this is very important, in code, what you should actually use is transpose convolution. Now, let me show you how this magic, now all of you are wondering, how would we pull this off? Isn't it? Anybody wondering about that? Yes. Okay. So let's try and do that. Suppose you have a little picture.
So is it matrix transpose you're doing?
Why don't we see? Why don't you see how we do it?
And transpose not the same.
See, guys, you're thinking matrices and matrix inverse and matrix transpose, right? None of them. Don't think of that. What it is, I'm just saying, wait and watch. I'm going to show you exactly that. I'm going to show you a piece of trickery that will manage to create a bigger feature map out of a small. And it is simpler than you think. So don't have nightmares of matrix inversions. You can do it without that. So here we go. Suppose I take a thing. Let's take something simple. 1, 2, 3, 4. Guys, remember that this is unrealistic. Why is it unrealistic? Typically, you end up with fractions. 0.2 minus 0.1, things like that. Right? But just to keep the things filtered. And remember, we have been playing around by 3x3 filters so far. Right? So let's go with our 3x3 filter, our usual 3x3 filter. Put in some numbers. What numbers do you want to put in? Let's say that we put in Can anybody tell what this is?
Not H.
Horizontal line detector.
Yeah.
Horizontal line detector. Let us say that it is there. Now what we do is, what we need to do is do something here to end up with something. Let's say this is 2x2, right? We want to do something that will produce, let us say, a bigger feature map. Let's pick a size. Let's say 4x4. Right? 4 cross 4. Now the whole question is, what in the world is this? Have we made the problem more precise? We have a filter. We have the original feature map. We want to produce a bigger feature map. And now what do we do with it? So let's stare at it a little bit. And we say, okay, typically we were putting the filter onto the this thing, but let's do one thing. Let's put let's put this thing onto the filter, this tiny thing onto the filter, the opposite way, right? So if you do that, take one. First thing you take one, right? And this is one, step one. Let's write this way. Step A, take this guy. This is one, and multiply the filter with it. Oh, by the way, while you are at it, you also do this padding business, because remember that when you were coming down, you were applying paddings, right? So you were, might as well go, let us go apply padding also. Why not? For fun. It looks good. And now what do we do? And we just make sure that padding, whatever values come there, we'll just ignore it. It is just sort of a border, right? Filter with it. Now what happens? If I multiply one with this filter, what will remain? The filter itself, right? Nothing is going to change, right? Now let us put the filter in this location. Let me use a different color. It's a 3x3 filter. Let me put this. So what will happen? 1 multiplied by this will become here. What will I get? What will I get here? 1 times 1 is 1. But we are ignoring it. So this doesn't matter. This doesn't matter. This doesn't matter. This doesn't matter. This doesn't. So the part of it that really matters is only this, isn't it? So I can put those values there. 0, 0, minus 1, minus 1. Are we together?
So there is one top middle value should be 0, right? 1 by 1 into 0. The top row.
Yeah, that's what I did. You notice that.
No, the top row, the middle element.
No, but I'm saying ignore it. Whatever it is, ignore it. If it is in the padding zone, ignore it.
Okay.
If it is in the padding zone, don't bother. Those values just don't matter. Right? Because remember, we are trying to create the inner feature map. Remember, anything, the real thing is we are trying to create this guy, just this area. We did the padding just for being able to slide the filters. So far, so good, guys. Are you with me? Now let's do one thing. You say, aha, I managed to fill this feature map a little bit. What next? Let's see what we can do next. Let me use a different color now. What color would be good? Green. Yes, let's go with green. Green. Step B. Which one should we take? This guy. 2. We took 2. And what you do, and by the way, here, I'll just take stride is equal to 2. Stride means the filter will always jump by 2 steps, let's say. So now, what do I have here? Take 2 and multiply. You notice that I'm repeating it. Multiply the filter by it. What will I get? I will get, if I multiply the filter by 2, what will I get? 2, 2, 2, 0, 0, 0, minus 2, minus 2, minus 2. Guys, is it making sense?
Yeah.
Right. Now, jump 2 places, and green guy is here. Here is this. Are you together, guys? Any problems? Okay. So now what I do.
Just a quick question, Asif. Why is the stride 2?
Because I choose to. You can make stride 1. It's up to you. Okay. I just happen to choose that. So, guys, there's a lot of freedom in when you upscale it, right? I just happen to make. The reason I did it, frankly, is because I didn't want to do every single step. Let's get to the point. Right? Hold on, guys. So now what happens?
No, my question is, we could have picked stride 3 and we could have finished the whole thing, right? That's also possible.
Right, you could have done that, yes. So anyway, I'll just put it here. Now what happens? Here you get two, but this is useless. This is useless. This is useless. And you get 2, 2, 0, 0, -2, -2. Isn't it?
Yeah.
Now what happens is, as you slide the filter, and now what you do is, what happens to -1 and +2? Just add these two guys. Keep adding. Right? Now, likewise, if I go with 3, 3 will go. Now, I hope you got the point, right? What will I do? Take 3 and multiply by the filter. And what will you get? 3, 3, 3, 0, 0, 0, -3, -3, -3. And where will it go and sit? Where will this guy go and sit?
The lower quadrant?
Go and sit here. Isn't it?
Mhm.
Yeah. And so, guys, I won't do that. And then you can do with 4 and so forth. But do you guys realize that by doing this process, I can actually fill what really mattered to me? Namely, I can fill values in the real feature map. Oh, what just happened?
The yellow region.
The yellow region, exactly. I managed to fill the values in the yellow region, isn't it? And so what have I done? I have gone from a 2 by 2 feature map, a 2 cross 2 feature map, pulled off rabbit out of the hat, pulled a rabbit out of the hat, and ended up with 4 by 4, 4 cross 4 feature map. So guys, do you realize that this was all very simple? I just had to have some rules to do it. Is it making sense? This particular method is the transpose of a conv feature map.
The more filters you apply, you just keep adding them.
Yeah. You just keep on moving on. So guys, from this, this is it. That's it. Yeah. So guys, what is the lesson here? You can go down, make smaller subsample, and you can invert it in some sense. Right? And again, people use different terminology. The terminology people very colloquially use. They say that, it was a process of convolution, so I'm deconvoluting. Right? But don't use the word. Like you make mean deconvolution in a logical sense, but because deconvolution word has been reserved already by one particular implementation, what you're really doing is transpose convolution. Albert?
So those x's are eventually zeros, or are they just empty?
No, you remove that. At the end of it, you just plug this out because the padding you erase. Right? You remember that this was just fake region, right? This region was fake. You have no intention of keeping it. You throw this away. What remains is your yellow region.
It's only to do the transpose.
It's only to do the transpose convolution. That's it. After that, all you end up with, and that's why I made this picture, that you went from 2 by 2 to 4 by 4. Padding has disappeared.
Not only because of that, because we applied the padding from the beginning.
Internally,
So
how we pull
otherwise,
how we pull the rabbit out of the hat. We have some tricks there, like we padded, we did some stride, we did this and that, but those are all secrets. Yeah? But all of those secrets are called transpose call. But the end result is we went from 2 by 2 to 4 by 4. Magically, we up resolve the image, up sample the image effectively. Go ahead.
Could you explain what the purpose of the padding is?
Oh, that's a very good question. If you don't pad, you realize that you won't end up with a 4 by 4. I wanted to end up with 4 by 4 from 2 by 2. You'll end up with probably, let me see, you will end up with 3. Actually, you won't be able to move at all. You may be able to, you'll be stuck.
And why are we making it into a bigger image?
Oh, why are we making it into a bigger image? Because we can. Right?
Like, there's no
No, what the explanations will come. That's the topic of today. Right? That is the topic of it. So guys, I will end this by saying you learned about 2 neural architectures. Or actually, let me finish it here. I want to finish this topic here. Guys, let me recap. Do we understand deconvolution? Colloquially, what you call deconvolution, or more specifically, or transpose convolution. This is transpose convolution. I taught you a particular way of like making a bigger image, bigger feature map out of a smaller feature map. And this particular trick or method is called deconvolution. Now, hold on to your question. Why would we want to do that? That is the crux. That's the whole topic of today, and we'll come to it. Any further questions, guys?
As if the spatial information that's derived based on these feature map values, in which quarter the values are, is that how it's maintaining that? Or decode?
Yeah, the deconvolution also preserves. If you notice that it does not tamper with local information, right? It does not. When you look at it, spatial information is still preserved.
So, and initially you talked about inverting.
Say that louder, please.
Initially, you mentioned about invert.
Yeah, by invert, I just meant opposite. I meant opposite. I didn't mean literal matrix inversion. I meant
so that
opposite.
is what we mean. You meant as transpose.
Transpose convolution. Yeah, that is it. So, guys, when we use the word invert, it depends upon which sort of world you come from. If you talk to mathematicians, they think of it as inversion. Why do they think of it as inversion? Because they are saying, hey, I am magically looking for a function that undoes it. Did I write that somewhere? I remember writing it somewhere. Yeah. Basically, I'm saying that, yeah, look at this. That somehow I need another function g, which logically sort of will try to get me back where I started from. Right? Restore in some sense, you can say. And that's what this transpose is about. Why we do that is the crux of today. But I hope you understand this very simple technique of deconvolution or transpose convolution. Yes.
So the input where we did 1, 2, 3, 4, is that a contradiction where we on our everywhere we move first one on the x-axis and the second row which have p and 4?
Yeah, that is the rule. That is the rule. Okay. That's how you slide. Remember, filters slide from the top left slowly down, right? How much you slide at each step is called the stride. Right? So when you go from 1 to 2 and the stride, we choose the stride of 2, it means from this cell to left to right, then here the filter will move 2 paces up. When we go from here to here, again, we'll move 2 paces down. That's a conscious, and it is your decision. So guys, play around with it. What happens if I took a stride of 1? Somebody asked. Somebody said, why are we wasting time? Let's take a stride of 3. What happens then? What would you have to make the padding in that case? Yeah, so you'll have to play with these things. Play and develop intuition. Guys, these are the building blocks of the subject. I would strongly encourage you to do, there's a German word for it. It's that Einstein used to use Gedanken experiment. What Gedanken experiment is to ask questions like, if a cow jumped over the moon, what is the escape velocity the cow needs? Right? Now you say from practical purposes, cows don't jump over the moon. But it's a thought experiment, right? As a physicist, we can say, all right, if a cow jumped over the moon, what would be its escape velocity, right, to get there? That sort of thing. So what I'm saying is, do your Gedanken experiments. Play around with it. Sit down with a piece of paper and work it out. If I take this as my feature map, this as my padding, this as my stride, what will I end up with if I deconvolute it? It is just games to play, right? But when you play it a few times, you do a few exercises, you develop a feel for it. Right? Otherwise, you run the risk of forgetting it all or getting confused about it all. So please try those. And with that, I'll end the topic of transpose convolutions if there are no more questions. Final call for any more questions.